Hello, my name is William Jacob Taylor, and this is my presentation for radio design. We'll start off my first slide. Sorry I couldn't do a voiceover. My laptop does not have built-in speakers. Figured this would be a little bit easier. So start off with the branch line coupler. We designed it using the standard branch line coupler topologies, where you got 50 ohm transmission lines and 35 ohm transmission lines. The vertical transmission line are the 50 ohm, whereas the horizontal ones are the 35. All of the lines are quarter wave loops long. Using this will ensure that ports 1 and 4 are isolated, and that the power coming from port 1 to ports 2 and 3 should be about negative 3 dB or 3 dB of loss. And in simulating and measuring, I got around I think it's negative 3.9 dB from ports 1 to port 2, and then negative 3.5 dB from port 1 to port 3. There also should be a 90 phase difference between the output ports of port 2 and port 4. And this was also seen in the measured and simulated, which were very close to 90, but not exactly 90. I believe they were about 82 or 86 degrees, which was fine. The other reason why the transmission lines are not straight is because one of the design constraints. We had to do it on a smaller board, so that way the traces had to be maneuvered. The next component that we designed was the Wilkinson divider. It needed to be this shape so that the resistor could actually touch each transmission line. This was kind of the suggested layout, so that's what I went with. This was designed using 50 ohm transmission lines and 70.7 ohm transmission lines. The measured and simulated phase shift for this was around 0. Or sorry, not around 0. It was around 0 degree difference between the two output ports, which was needed. Also, there should be a 3 dB loss between the input and output ports, which was seen in both the measured and simulated. The measured for the top output port was, I believe, was negative 3.21 dB, whereas the bottom was negative 3.38 dB. That was pretty much standard, but the next component that we designed was the mixer. It was a double balance mixer, consisting of surf mount components, 2 balance, 1 IC or integrated chip that consisted of 4 Scotchy diodes. As you can see, the tested results on the VNA was pretty much that. It wasn't the best mixer, but that was also due to some pretty bad soldering between the RF and IF ports. The LO was much easier to solder since it was over there by itself. I had a little bit of difficulty soldering the RF side mainly, and the balun, to be specific, to the ground pad once I had all of the other components mounted. And I believe that was contributed to not the best result, but still a result that worked. I believe that it was around negative 25 dBm for one of the mixers and negative 19.3 dBm for the other mixer. And ideally, the sidebands would be taller than the IF. The next was the power amplifier. It was the most difficult design. The biasing circuit was already set up for us in the template, so that's what we went with. We just had to solder all of the surface mount components, which was no big deal. We did perform load pulls, so that way we'd get the optimum for the output matching network. So the optimal load that I got from the load pull was about 251 plus 132J. I was able to get very close by modifying lengths of the output transmission lines, which were I cannot remember the lengths, but I got around 235 plus 123J, which was pretty close, so I was pretty happy with that. The input matching network was just the complex conjugate of the small signal impedance, and so that was pretty easy to get. That was pretty easy to design with, and also I got pretty close to that input matching network value as well by just modifying the lengths of the transmission lines. We printed it out and then I tested it, and I was kind of shocked by how bad it did compared to the simulated results. I think the simulated gain was around 18.5 dB, whereas whenever I actually went out there and measured the gain, it was around 7.5. So I had about 11 dB difference between the two. And as you can see, my actual layout could be due from me designing the trace to go over top of the word input, so it was additional metal that the transmission line came in contact with, which was not good, and I actually didn't consider that whenever I was designing it. The other possibility is that the output transmission line, specifically the one on closer to the outer edge, probably should be closer to the U-shaped. That could be an additional reason why it did not perform as well as it was simulated to. That was pretty much all about the power amplifier. Next was the antenna, which was the easiest design. We designed it using the antenna synthesis software from NI, and more or less you went in there and played around with the different types of antennas that you could build. They had several. I actually simulated about 8 of them, and this is one that I found I was pretty happy with. Output gain, and also the loss or the reflection coefficient, which was around negative 20 dB, both measured and simulated. We went to the lab with GNU and simulated in the antenna chamber. That was pretty neat. I've never been inside one of those, and I thought that was pretty neat. The simulated gain was around 5 dB, the simulated gain was around 4.6 in the software, and the actual measured gain was around closer to 5. Using MATLAB, I actually got the actual max, which was 5.01 dB. And those are some of the plots that show that the measured reflected coefficient for 0.95 megahertz or 950 megahertz was right around minus 18 dB, which was good, and then the gain was around 5 whenever it was directly in front of the receiving antenna. This was the full radio system demo. That was the output. As you can see, it's not completely square, but that's because my mixers were not this identical. So one of the reasons that we had to do this was one of the input voltages to the LO was, I believe, 200 millivolts peak to peak, whereas the other one was 350 millivolts peak to peak. That was the whole setup. You can see the antennas in front of each other and everyone else not around it to mitigate any other type of interference. That was kind of a close-up on all of the radio connected up together. You got the branch lines connected to the mixers, and then the LOs going out of there, connected to the Wilkinson, and all of that had to be, connected straight together. And then that goes into the input of the PA, powered by a 9-volt battery, and then out to the antenna that we made, or that I made, and that was the full system demo, and it did work, so I was pretty happy with the result. I enjoyed the class. Thanks, and bye.